Welcome everyone. In this video I will show a useful method that can be used while calculating the total kinetic energy of a rotating rigid body. Let's draw ourselves a rigid body. Perhaps it looks like this. And let's choose a center of mass. Where should it be? Let's choose it like this. This is the center of mass. Now, at this instant, the axis of rotation, the instantaneous axis of rotation, is perhaps this axis, which I call I. So this is the moment of inertia with respect to that axis of rotation. The distance from the center of mass to our axis of rotation will be r. Now, I claim if I want to calculate the total kinetic energy of this rotating body, I can basically do 1 over 2 I times omega squared. Well, omega squared is, of course, the angular velocity around this axis of rotation. This is my claim, and I will prove that this is correct in this video. So how do we start? To start, since we are interested in the total kinetic energy, I want to split it into two parts. Total kinetic energy is equal to kinetic energy that is translational plus kinetic energy that is rotational. What is the translational kinetic energy? It will be 1 over 2 m v squared. M is the mass, v is the speed, and we put the subscript cm, center of mass. This is the velocity of the center of mass, mv squared. Plus 1 over 2 I center of mass. This is the moment of inertia of the center of mass. Then we multiply this by omega squared. So far so good. Here I will use an important idea of rotational motion. That is, velocity at any point is equal to omega times the distance from the point to the axis of rotation. This is the general formula. If we change this to suit our purposes, we say we will be interested in the center of mass velocity. This is equal to, well, what is omega for center of mass? It is still omega because we are interested in a rigid body. All points have the same omega for our case. And x will be r because we defined it right here as the distance from the center of mass to the axis of rotation. And now I will substitute this guy here to get 1 over 2 m omega squared r squared plus 1 over 2 I center of mass omega squared. This will equal. Here I want to factor out 1 over 2 omega squared. That will leave us with m r squared from the first term and I center of mass from the second term. This is very helpful because by the parallel axis theorem, this part will give us I, right? The parallel axis theorem tells you if you want to calculate the axis of rotation, at any point you get the axis of rotation that passes through the center of mass and you add mr squared, where m is the total mass and r is the distance from the point from the axis of rotation to the center of mass. This is correct by the parallel axis theorem, which I can do a video about if you want. So you can leave your suggestions in the comment section. So enough said. From this, of course, we get the desired result 1 over 2 I omega squared. Good. Here I want to make a very important alert, very important mention here is that this I is not the center of mass's moment of inertia. I know it might be obvious from this derivation, but believe me, in lots of problems, all of us often make that kind of a mistake. What I'm saying is, if we have a wall like this and let's say that there's a rod rotating, this will be the axis of rotation perhaps. In that case, you should use the I value that comes with that center of rotation, with that axis of rotation. Excuse me. You shouldn't say this is my axis of rotation, ICM, and I will use it. No. If you do that, you get the wrong result. And by the way, if you really want to do that, well, you can. You then need to use this sum, which isn't very complicated, but if you know what you're doing and if you pay attention to the axis of rotation that you choose, you can use this shortcut. I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.